All right, so this is 11.4, the comparison test. Now, we've actually talked about this a little bit in the last couple of sections before, but now we're getting far more in depth of the comparison test itself, or comparing two individual values itself, okay? So what we do is we'll compare series to series, and depending on the situation, we can actually see if it converges or diverges. Now, what I mean by this little joke here, then pray and it goes our way, is the limited comparison test could be a really good blessing or a horrible, horrible mess when it comes to it. And here's the reason why. So it says the limited comparison test is, suppose we have the series a sub n and b sub n with positive terms. Okay? One says if the series of b sub n is convergent and a sub n is less than b sub n for all n, then a sub n converges. So what this is saying is, if we can find, so let's suppose a sub n was our original question we're dealing with. Okay, this is the question that asks, okay, does a sub n actually converge or diverge? Number one says, if I can find a series that's actually bigger than the original we started with, and the one we found out, the bigger one, it actually converges. Therefore, by default, the small one also converges. And so that's what it means there. So basically, we have to find a series that's bigger than what we're actually starting with, and prove that this converges. So therefore, by default, that converges. So that's what number one says. Okay, and number two says the complete opposite. If I can find a b sub n that diverges such that b sub n is now smaller than our original function, so now if I can find a smaller function, and if I prove that actually diverges, therefore the bigger one also diverges, the original one. Okay. Now this is a very key concept when it comes to it, because it can get a little confusing because of one thing. If we find one that's bigger than the original, and if we find out that this diverges, that doesn't mean 2 is correct, right? This diverges, so therefore we do not know about the smaller one. So that's why you got to be careful how this comes into relating one another. So when it comes to the comparison test and comparing it to one or the other, the best way you want to deal with it is go with a plan of action, meaning, okay, I want to prove or show it actually converges, and somehow maybe you actually find out you actually diverges in one or the other. So that's the plan. You want to figure out a way that, to show, okay, does one actually work? If one does not work, therefore, okay, now I've got to find another one for part B. So because obviously it's going to be one or the other, right? Either converges or diverges. Now it's up to you how you want to do with it. I usually like to check, okay, does it converge first? And if I can't do that, therefore, can I find a one that actually diverges? Or vice versa. You could start with this one and then see if it doesn't diverge, therefore you know it's going to converge it. You got to find out that individual sequence itself. Okay. Now, obviously there's thousands and millions of series out there, and how do you know what to compare it to? Now, this is the easiest of the two we can deal with. In most cases, you always want to compare it to a p-series test and a geometric series when it comes to want to figure out if it converges, because we know a geometric series converges and a p-series converges or diverges depending on the situation we actually have, right? So the p-series one relates, so the p-series relates to the 1 over n to the p, and the geometric is r to the n with a, right? Where if r is less than 1, therefore it diverges. If r is greater than 1, it also, it diverges, right? That's the process we're going to be dealing with there. Okay. All right, so let's try this out. So again, these are going to be pretty much, hit and miss, and you got to get comfortable of the situations at hand. Okay, so let's determine the series converges or diverges using the comparison test. So we're going to compare some other sequence to this. Okay. Now, like I said, the whole goal is, okay, I want to see, okay, I'm going to try to prove it that converges. That doesn't mean it's going to work, but that's the game plan. If you prove that it doesn't converge, therefore it's going to diverge for sure, right? You just got to figure out how to figure out that sequence itself, okay? So I'm going to know what the game plan is. This is going to converge. So what I'm going to first do is I got to find a series that's actually bigger than the one we actually have. Okay? Now, this comes a little finesse as well, okay? And what I mean by finesse is like this. So I'm sure you all agree that this side is bigger than that side, right? For all n, right? For any n you put in, it's going to be bigger than the other one, okay? Now this is what I mean by some finessing. So remember, I want to somehow have this a sub n to be smaller than this 2 series I have here. Now, when you flip it and put it into a fraction format, like this, now the inequality actually flips as well. Okay? Which would make sense, right? For example, 5 is bigger than 3, right? That's for sure. But if I flip the fractions, 1/5 is actually smaller than 1/3, right? So the inequality actually flips. Same process is happening here. Okay. All right, so again, remember, I want this to look like this. So the only thing that's missing for my sequence right here is just multiply by 7. So let's multiply both sides by 7. And we get exactly our b sub n we're going to be dealing with in this question. Okay. So this is our a sub n. This is our original function, a sub n. And this is going to be our b sub n in this process. So again, remember, my goal was to show that this actually converges. So the whole goal now is to show that this actually converges to a number. And if we do that, therefore this converges. If this diverges, well, guess what? Back to the drawing board. That means I have to pick another sequence that probably converges. Or, the worst thing is, I've had these people in the past is, well, it works for one series but doesn't work for the other, meaning you have to find another series that's actually bigger that does actually converge. So it's not always a hit or miss kind of thing. It's a lot of it is just going to be finessing when it comes to this type of test. Okay, so we could find out if this series converges, we're pretty much done, right? So we got to test or show that if this series converges. Okay, so what I'm going to do is just going to rewrite this a little bit. Make it look like that. Okay. Now, do you notice something very particular? Right? We always want to compare it to the p-series and geometric series, right? And notice we actually have a p-series here. Well, actually, if you want, you can even use a geometric series as well. R is just 1 over n. In this case, so if you want, you can use geometric because a could be 7/2. But it really doesn't matter because you bring this to the outside, and you have either your p-series or your geometric series itself. And there's your p-series, right? P is equal to 2, which is greater than 1, so therefore it converges. So therefore the original converges based off that. And again, you could also have done the geometric series where R is equal to 1 over n. Oh no, you couldn't do that because it's not to the n power. Sorry. Yeah, P series is the way to go. Okay. So notice we never even touched this stuff, right? You want to compare it to something you know that you can somehow manipulate in a way you want it to. Okay, let's look at this one. All right, so just for fun, I'm just going to flip it. So I think maybe this kind of converges or diverges. I'm going to pick diverges and see. So I'm going to try to show that number 2 is actually correct. So that means what I'm saying is I got to find a series that's smaller than the one I have and show that this diverges, right, the smaller one. So I'm going to do the complete opposite method I just did here. Okay. So remember, my whole goal is to find something smaller than this. Okay. And again, notice I always start from the bottom, so I'll just start from the bottom here. Okay. Well, I know this is definitely smaller than or equal to the square root of n, right? It would make sense, right? If you're subtracting 1, it's definitely going to be smaller than what you originally started with, so I know that's true. And so when I flip it, again, flip sign, and now we have something here, right? So this is our a sub n, our original, and this is going to be our b sub n. And notice it satisfies the condition, right? The b sub n we have is strictly less than or equal to our A sub n value. Okay. And again, right, since I'm using 2, I have to show this actually diverges. Now, if I actually show this converges, again, that does not mean A sub n converges, because I just showed that something smaller than it converges, right? I actually have to find this condition, so be very, very careful of doing this process. So just because you have a contradiction doesn't mean the other one automatically applies. Okay. All right, so now we got to show that this series converges from n equaling 1 to infinity of 1 over the square root of n. Okay. And again, I really like the square roots. I always like to put stuff into its exponential form, which makes it much easier to look at. Okay. Now again, hopefully you notice something very nice. It's also a p-series. So in this case, p is equal to 1/2. And again, according to the p-series test, since 1/2 is less than 1, so therefore this automatically diverges. All right, so we got it checked. So we showed that something smaller than our original diverges. So like, it goes to infinity. So something bigger also goes to infinity, right? It would make sense it could be even bigger. So therefore, the original of A sub n here also diverges. Okay. So again, the comparison test is very, very interesting in that process. You just got to be, it's hit or miss. Sometimes it takes you like 2 minutes to do it. Sometimes it makes take you 20, 30 minutes to do a question. And it just depends on the series you actually use. Okay. Now, another test which actually is not as difficult, well, I don't think it's as difficult, is called the limit comparison test, which in most cases a lot of people actually like itself. It's a little easier to deal with, and it's kind of straightforward itself. Okay? So the limit comparison test says, suppose that we have two sequences, A sub n, B sub n, with positive terms. This one says, if I take the limit of the division of the two series and they equal a value c, where c is finite, and greater than 0, which is a key thing. It has to be greater than 0, strictly greater than 0. Then either both series converge or both series diverge. Okay? Now again, this is very similar to the comparison test because now again, we have to find a b sub n. Now the condition b doesn't have to be bigger or smaller than it, but if we could find a b sub n, and if I know automatically that b sub n converges, diverges, and if, again, I do this portion to get a value, automatically one of these is going to be true. So if I show, so first say this diverges, right? I know this diverges. I plug it into here, it gives me like infinity. Therefore, because this diverges, therefore that diverges. Okay. On the other hand, if I know b sub n converges, and I get a value of like 7, therefore, since this converges, also that converges. Okay, so that's what the limit comparison test is all about. It's going to be both of them, or none of them going to happen when it comes to it. So that's a key thing as well. Okay. So how we use this. So again, finding the b sub n isn't as difficult. You always want to compare it to something you know how it converges, diverges, right? And things like that. So let's try an example so you can see how this works. So determine the series converges, diverges. And again, we're going to try the limit comparison test. So this is going to be our a sub n, right? This could be the top of the function there. Now we're going to figure out a b sub n. Okay, and same process. You're either going to pick a b sub n that you know converges or diverges, and then from there you're going to go from what happens in the situation we have at hand. Okay. So when it comes to a divergent series, you want something similar to what we have because you're going to take the limit, right? So taking limits of something that's really complicated is going to take even more harder to deal with, right? So you want to do as little work as possible when it comes to it. Now, what I like to do is just compare it to something not as difficult as what we have, right? So like the bare basics. So if you noticed, this is very similar to something like this, right? And I know this converges because if I just rewrite this, it looks like that. And I know this is a geometric series. So this converges because R, in this case, is less than 1. So I know it converges. Okay, so like I said, right, even with this one, you always want to compare it to a p-series or geometric series in this case. Okay. Now I could have done like 5 here, 3 here. I just decided to kind of make it look almost exactly what we had to begin with. Okay. So now I chose one that converges. So there, hopefully, when I take this limit, I get a value. So therefore, by default, because this converges, the top will converge as well. Okay. So let's try this out. So let's take the limit as n goes infinity of this divided by this. Okay. So this is a complex fraction, so I'm just going to rewrite this. All right, so notice the 3's cancel. This becomes the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Okay. Now, fun little trick, I don't want to call it trick, it's just a concept that always becomes true, is essentially, since we have the same thing top and bottom, right, this minus 1 doesn't really do much to it. This will end up being 1, actually, when we take this limit. Now, if you're wondering, okay, how does that work? How do I know that's going to be true? Is if we take, this goes to infinity, this also goes to infinity. So again, you can use L'Hopital's rule. So L'Hopital's rule takes just take the derivative of top and bottom individually, and this is going to be the derivative to the n is going to be 2 to the n natural log of 2. If you do the same thing on the bottom, right, that 1 goes away, and look what we get. Exactly 1, right? They can just cancel each other out, which is key because this is strictly greater than 0. So therefore, because our original function we compared it to b sub n converges, because it's geometric, therefore a sub n also converges because it says either both converge or both diverge. So therefore, this converges. There we go. Okay. All right, let's try another example. This one's a little bit more complicated itself. Okay. All right, look at this horrible mess. So the sum of n equal 2 of all that fun stuff. Okay. Okay, now there's a trick here when it comes to finding if I can, notice there's a lot of tricks, right, when it comes to it. As you noticed here, I compared it to something very, very similar to what we had originally, right? And that's kind of the idea I want to deal with here. Okay. And in most cases, you want to keep the highest power in your comparison. So for example, I want b sub n to be the highest power on top is usually 5n squared. Okay. And the highest power on the bottom, which is going to be here, is n to the 5th over 2 power, right? Because it's in the square root. Okay. And if I just simplify this a little bit, this is equal to the sum of n equaling 1 to infinity. And again, just rewriting this a little bit, is 5 over n to the 1/2 power. Okay. Now notice, this is a p-series which diverges, right? P is equal to 1/2 less than 1, so this diverges. All right, so, okay, it looks like my goal is now just to show that this diverges. Again, just using this process of diselimination, I didn't think it would kind of diverge, but, it just so happened. So I'm just going to go with it and see what happens, right? And if it doesn't work, go back to the drawing board, unfortunately, to deal with that kind of stuff. So let's see what happens. So we're going to take the limit. N equals to infinity. What am I doing? This on the top. Times, and I'm just going to flip it to make it easier. just do it like that when it comes to it.